Hello everyone. On this video we will be going over using property of logarithmic equations and exponential equations. Okay, so starting off we will look at the one-to-one property of logarithmic equations. Let me straighten that up a little bit. Logarithmic equations. Okay, so we have the one-to-one property of logarithmic equations. Okay, so what if we let the capital M, let's say if we know that that's positive or greater than 0. So if we let the n be greater than 0, and our base is greater than 0, but we know that the base doesn't equal 1. Okay, so we have all four of these things that have to be true. M and n are both positive. Base is positive and not equal to 1. So if log of base b of m equals log base b of n, then m has to be equal to n for that to be true. Okay, so that's your one-to-one property of logarithms. All right, so let's say, for example, if we wanted to solve, let's say 3 times log base 3 of x equals log base 3 of 27. Okay, so let's say we wanted to solve that one for x. Okay, now we can't use the one-to-one property because you have that coefficient there. Okay, so the first thing we want to do is use the power rule of logarithms to get rid of the coefficient. Okay, so that means that 3 from the power rule gets moved up there. Alright, so just writing where we're starting off, so you have 3 times log base 3 of x equals log base 3 of 27. Remember, that just becomes an exponent, so you now end up with log base 3 of x to the third power equals log base 3 of 27. Okay, now the one thing you want to look at is the fact that you have log base 3 here and log base 3 here. Okay, so in order for this to be true, x to the third power has to equal 27. Okay, so now we just take the cube root of both sides. Okay, so if we take the cube root of x to the third power equals the cube root of 27. Remember, your cube and your exponent and your index cancel out, so you end up with x equals the cube root of 27 is equal to 3. Okay, so that's how you would solve this one. But the one thing you want to be sure to do when you get your answer, and this is one of those things that it's not optional because you could solve it and you could still end up with the wrong answer if you don't check it. Check by plugging into the original equation to make sure there are no negative values. Okay, Now the thing is, sometimes it's optional to check. When you're doing logarithmic problems, it's not optional. You actually have to check it, because there are times that you may solve for an answer, but if you plug it in, you'll end up with a negative value here. Now this one, you plug in x equals 3, that one's okay because you have log base 3 of 3, and you're good. It's not negative. But we will have some examples to where you'll see that if you plug in your answer, you will end up with a negative log value, and that you can't use it. Because remember, the m and the n both have to be positive. All right. So if you're still writing, feel free to press pause. But we're going to go ahead and go to our next example. All right, bring that down. All right, so let's say, for example, we want to solve 2 times log base 5 of x equals log base 5 of 169. All right. So just like before, we're going to use the power rule to get rid of that coefficient. Of the coefficient. Okay, so all that means is that we'll start off with 2 times log base 5 of x equals log base 5 of 169, but using the power rule, that 2 is just going to go up here. So we have log base 5 of x squared equals log base 5 of 169. All right. So you see here we have log base 5 here and log base 5 here. So as long as those two are the same, we know that x squared has to equal 169 for this to be true. So we have x squared equals 169. Okay, so we go ahead and square root both sides to solve for x. So square root of x squared equals the square root, well, plus or minus the square root of 169. Okay, so the square root of 169 is 13. The square root and the square cancels each other out. So you have x equals plus or minus 13, which you can rewrite it as x is equal to 13 or x is equal to negative 13. All right. So here you're about 99% done, because now you have to remember to check. Okay, so if we plug in x equals 13, replacing x with 13, you're good. You don't even have to go through all the answers. You just want to make sure it's not going to be negative in there. So you plug in x equals 13, you're good. You plug in x equals negative 13, you're not good. Remember, that value cannot be negative. So you can't use that negative 13. Okay, so this one's not a solution, since, let's say 2 times log base 5 of negative 13 equals log base 5 of 169, remember that that m has to be greater than 0. Okay, so if you plug in negative 13, that m is no longer greater than 0, so you have an undefined solution. So x equals 13 is your only solution. Okay, so even though you started off with 2 solutions, the only valid solution that you can use for this problem is x equals 13. So that's why you always check your answer. Because I hate for you to do like a lot of work. Some of these problems can take a lot of work. And then right at the very end, because you didn't double check your answer, you end up getting it wrong, and I don't want to see you do that. All right, so let's go to our next example. Let's bring that down a little bit. All right, so let's say, for example, if you want to solve, say, log base 5 of 4x minus 5 equals log base 5 of 3. All right, so here if you notice, there's no coefficient, so you don't have to worry about the power rule. Okay, so you can just go right past the power rule. So if you have log base 5 of 4x minus 5 equals log base 5 of 3, you have log base 5 and log base 5. So this is only true if 4x minus 5 equals 3. Okay, so if we go ahead and solve for x, add 5 to both sides. You have 4x equals 8. Divide both sides by 4. You have x equals 2. And remember, if you plug it in, and remember, you don't have to write it out. If you just plug in x just to make sure it's not negative, you're okay. So if you have x equals 2, you have log base 5 of 4 times 2 minus 5 equals log base 5 of 3. Okay, so you have log base 5. 4 times 2 is 8. 8 minus 5 is 3. So equals log base 5 of 3. So you're good. Okay, so this solution is valid. All right. Okay, so if you're still writing, feel free to press pause. We're going to go ahead and go to our next example. Okay, so let's say, for example, we want to solve, say, log base 2 of x plus log base 2 of x minus 3 equals 2. Okay, now if you see here, that plus sign kind of throws things off a little bit. Okay, so if you notice, not in the form of log base b of m equals log base b of n. Okay, so since it's not in the form of that, the one thing you want to do is, we see that plus sign, so we know we can use the product rule. Okay, so if we apply the product rule of logarithms, we see that log base 2, I'm just going to rewrite it, plus log base 2 of x minus 3 equals 2. You see here that plus sign, again, using the product rule, that becomes log base 2 of x times x minus 3 equals 2. Okay, so we won't always be able to apply our rule for logarithms, or our one-to-one rule for logarithms. All right. Now from this step, if you remember that log base b of x equals y, remember that's equivalent to b to the power of y equals x. So your base to the power of your answer equals x. Okay, so that gives us our base to the power of y, so 2 to the power of 2 equals x times x minus 3. Okay, so now that one will be a little easier to solve. Okay, so if we go ahead and distribute that x, and I'm just going to flip it around because I like my variables on the left. So x times x is x squared minus 3x equals 2 squared, which is 4. Okay, so if we go ahead and subtract 4 from both sides, you have x squared minus 3x minus 4 equals 0. Okay, so once you do that, you don't have to worry about anything else because now you just factor. Okay, so if you go ahead and factor, you end up with x minus 4 times x plus 1 equals 0. Now once you have that, all you have to do is just set both of those equal to 0 and you'll have your two answers. Okay, so you have x minus 4 equals 0 or x plus 1 equals 0. Alright, so if we go ahead and add 4 to both sides here, you have x equals 4, or if we subtract 1 from both sides here, you have x equals negative 1. Okay, now remember, once you get your answer, you want to check to make sure that if you plug it in, you won't end up with a negative value inside your log. So if you plug in 4, you get log of 4, log base 2 of 4, and 4 minus 3 is 1, so log base 2 of 1, you'll be okay. If you plug in negative 1, as soon as you get it in there, you automatically see log base 2 of negative 1, can't do anything with it. Okay, so you can't use since plugging in will give a negative log value. Okay, so x equals 4 is actually your only solution. Okay? Okay, so that's why that double checking is very important. Alright, so let's go ahead to our next example. Remember, if you're still writing, feel free to press pause. Alright, so let's say for our next example, if we want to solve, say, log base 5 of x plus 3, plus log base 5 of x minus 6 equals log base 5 of 10. Okay, so once again, that plus sign is kind of throwing us off a little bit. You can't put it into the form that we would like. So can't put into log base b of m equals log base b of n form. Well, actually you could, but you can't do it without a little manipulation. Okay, so if you notice here, you have the plus sign. Okay, so if you have the plus sign, and I'm just going to rewrite it, log base 5 of x plus 3 plus log base 5 of x minus 6 equals log base 5 of 10. That plus sign means you can use the product rule. So if we apply the product rule of logarithms, you have log base 5 of x plus 3 plus log base 5 of x minus 6. That's going to equal log base 5 of x plus 3 times x minus 6 equals log base 5 of 10. Okay, so what that shows us is that now we have it in our log base b of m equals log base b of n form. Just had to manipulate it a little bit. Okay, so we have log base 5 here and log base 5 here, which means this will only be true if this is equal to that. Okay, so we know that x plus 3 times x minus 6 has to equal 10 for this to be true. All right. Okay, so we go ahead and do the FOIL method on this side. We have x squared minus 6x plus 3x is minus 3x minus 18 equals 10. Okay, so if we go ahead and subtract 10 on both sides, we subtract 10 on both sides, we have x squared minus 3x minus 28 equals 0. And that disappears. Okay, so we go ahead and factor this left side. We'll end up with x minus 7 times x plus 4 equals 0. Okay, so we go ahead and set both of those to 0. So x minus 7 can equal 0, or x plus 4 can equal 0. Clean that up a little bit. So if we add 7 to both sides, we have x equals 7. We subtract 4 from both sides, we have x equals negative 4. Okay, so if we plug these into our original equation, if we plug in 7, you have 7 plus 3, which is 10. You have 7 minus 6, which is 1. So that's 7 is good. If you plug in negative 4, you see right here, negative 4 plus 3 will give you negative 1. So you can't use negative 4. Now, it doesn't mean that all of them have to be negative. If you have just one negative logarithmic term, you can't use that value. Okay, so not valid since plugging in gives a negative log value. Okay, so x equals 7 is your only solution. Okay, so once again, the checking comes in very, 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 very handy. All right. So again, if you're still writing, feel free to press pause, but let's go to our next example. And separate these, papers are sticking together. There we go. All right, let me slide that down a little bit. Okay, so let's say for this example, let's say if we want to solve log base 7 of x plus 7 plus log base 7 of x plus 6 equals log base 7 of 6. All right. So what I want you to do is I want you to press pause and solve this one. Okay. Now the steps are pretty much identical to the previous example, so you can kind of use that one as a guide. Okay, so go ahead and press pause and work this one out. Alright, so I'm assuming you've already pressed pause and worked this one out. So let's go ahead and verify your answer. Okay, so we have log base 7 of x plus 7 plus log base 7 of x plus 6 equals log base 7 of 6, which is I'm just rewriting it. Okay, so we see here that plus sign means you can use your product rule. Okay, so those two terms will just combine to give you log base 7 of x plus 7 times x plus 6 equals log base 7 of 6. Alright, so you see here we have log base 7 and log base 7. So that means this can only be true if x plus 7 times x plus 6 is equal to 6. Okay, so just like before, we can go ahead and FOIL this one out. So we have x times x, so we have x squared plus 6x plus 7x, so that's plus 13x plus 7 times 6, which is 42, is equal to 6. Alright, so if we go ahead and subtract 6 from both sides, we will end up with x squared plus 13x plus 36 equals 0. Okay, so if we go ahead and factor this side, that would give us x plus 9 times x plus 4 equals 0. Okay, so we go ahead and set those to 0. So x plus 9 can equal 0, or x plus 4 can equal 0. Okay, so if we subtract 9 from both sides, we have x equals -9. If we subtract 4 from both sides, we have x equals -4. Okay, so now we plug both of those in and we check. Okay, so if you see here, if you plug in -9, you have -9 plus 7, that will give you log of -2. Okay, so we can see here, we automatically know we can't use that one. Plugging in gives a negative log value. Okay, so we can't use that. Sorry about that. Okay, so we know we can't use the x equals -9. If we plug in -4, and, well, this is the same answer here. If you plug in the -4, you have -4 plus 7, which is 3, so log base 7 of 3 is okay. If you plug in -4 here, you have log base 7 of 2, so that's okay there. So you're actually okay with the -4. Okay, so this is actually your only valid solution. Okay, I mainly wanted to do this one because if you look at the previous examples, whenever you had a negative number, it always ended up being not a valid solution. I wanted to show you that your answer can be negative and still be a valid solution. Okay, it's all about after plugging it in, what do you end up with? All right. Okay, so if you're still writing, by all means, feel free to press pause, but let's go ahead and move on to our exponential equations. Okay, so we solved our logarithmic. Now we're going to solve our exponential. Okay, and I kind of pre-wrote these steps. Okay, so when solving your exponential equations, the first thing you want to do is you want to isolate your exponential expression. As you can see, that's very important. It's always going to be your first step. Okay. Now, second, if necessary, because in some cases it won't be necessary, but if it's necessary, take the common logarithm or the natural logarithm on both sides and use, that should be used, it looks a little bit ran together here, so let me clean that up, and use the power rule to rewrite as a factor. Then you're going to solve from there. Okay, now 3, you want to check the solution in the original equation, and here it's kind of optional, but it's one of those good habits. Okay, with the logarithms it's not optional, but with the exponential it's kind of optional, but it's still a good habit to get to. Okay, and remember, we have the natural log of e to the whatever power that is. The natural log and the e cancel each other out, so you're only left with your exponent. All right. Okay, so if you're still writing, feel free to press pause. But we're going to go ahead and go to our first example to show you how this all works out. Okay, so let's say, for example, if you want to solve, let's say 6e to the power of 2x equals 24. Okay, so remember your first step. You want to isolate your exponential value. So if you have 6e to the power of 2x equals 24, we're just going to divide both sides by 6. Where anything divided by itself is just 1. So you have e to the power of 2x equals 24 divided by 6, which is 4. Okay, so now your second step, you want to apply natural log to both sides. Okay, so if we have e to the power of 2x equals 4, that means you have the natural log of e to the power of 2x equals the natural log of 4. Okay, now if you remember, we have natural log of e to the whatever, the natural log and the e cancel each other out. So you're left with 2x equals the natural log of 4. So if we want to solve for x, we divide both sides by 2. So we have x equals the natural log of 4 divided by 2. Okay, now this is your exact answer. But in some cases, they will want you to give that answer as a decimal. So if you plug that into a calculator, you end up with x equals natural log of 4 divided by 2. It's not equals, it's more of an approximation. So we use the little squiggly equal sign for the approximation. So 0.693 if you plug that into a calculator. So a rounded decimal answer. Okay. Now in most cases they'll tell you what to round it to. They'll tell you to round it to the nearest thousand, so 3 decimal places. So you just have to pay attention to the instructions and they'll let you know just how big to make that decimal. Alright. Okay, so again, if you're still writing, feel free to press pause. But we're going to go ahead and go to our next example. Uh-oh. Alright, so let's say, for example, if we want to solve, say 2 times e to the x plus 2 power equals 32. Okay, so 2 times e to the x plus 2 equals 32. Alright, so just like before, your first step, you want to isolate your e value. So if you have 2 times e to the x plus 2 equals 32, we're just going to divide both sides by 2. Okay, so that gives us e to the power of x plus 2 equals 16. Alright, so now we go to our second step, where we apply the natural log to both sides. So if we apply natural log to both of those sides, we have the natural log of e to the power of x plus 2 equals the natural log of 16. Okay, so remember the natural log and the e cancel each other out. So you have x plus 2 equals natural log of 16. Okay, so if we subtract 2 from both sides, we end up with x equals natural log of 16 minus 2. Okay, remember that's your exact answer. But if we plug that into a calculator, we'll end up with x, or an approximate value of x equals 0.773. Okay, so that's your decimal approximation. Okay, so like I said, it all depends on what particular answer form they want you to put it in for that particular question. All right. Okay, so if you're still writing, then feel free to press pause. Let's go to our next example. Go ahead and bring that down a little bit. That's what we should. There we go. All right. Let's say for our next example, if we want to solve the e to the power of x plus 2 minus 1 equals 9. Okay, so now what I want you to do is press pause and solve this one using the same steps that we used on the previous one. Alright, so assuming you've pressed pause and already worked this one out, I'm just going to rewrite it. Remember, your first step is to isolate your exponential value. So you have e to the x plus 2 power minus 1 equals 9. On this one, you just add 1 to both sides. And that gives you e to the power of x plus 2 equals 9 plus 1, which is 10. Okay, so you have your e value isolated on the left side, which brings us to our second step, which we apply our natural log to both sides. Okay, so if we apply natural log to both sides, that gives us the natural log of e to the power of x plus 2 equals the natural log of 10. Okay, remember, your natural log and your e cancels out. So that gives you x plus 2 equals natural log of 10. Okay, so if we subtract 2 from both sides, we have x equals natural log of 10 minus 2 as your exact answer. Or if you plug that natural log of 10 minus 2 into a calculator, you will end up with x is approximately equal to 0.303, which is your decimal approximation. Okay. So once again, it all depends on what answer they ask you for. Okay, so be sure to definitely read the problem carefully. Okay, so now let's go into a couple of story problems. Okay, so before we go into our story problems, for those who may have forgotten, we're going to take just a quick look at compound interest. Okay, so if we let the value p equal your principal, that's basically your starting amount. Okay, let r equal your interest rate, which of course you want to convert that to a decimal form to use in our formula. Okay, we'll let t equal our time in years, and we'll let a equal our new amount or our updated amount. Okay, now when you want to compound your interest a certain number of times per year, this is the formula you will use. Your amount is equal to your principal times 1 plus your interest rate over the number of times per year you're going to compound it, and that's going to be raised to your compounded number of times times your year, or in your time in years. Okay, so that's your compound interest formula. Now, when it's compounded continuously, that's when your amount is equal to your principal times e to the value of your rate, of course, converted to decimals, times your time. Okay, so you have your compound interest and your continuously compounded interest. Okay, so of course, if you are still writing, feel free to press pause and write down the formulas that you will need to finish up on, and we'll go ahead and go to our first example. Okay, so let's say for this example, let's say that we know that Joe invests $9,000 at age 18. Okay, so when he was 18 years old, he invested $9,000. Okay, so let's say that he hopes it will be worth $18,000 when he turns 30. When he turns 30. Okay, now if the interest is compounded continuously, okay, so that compounded continuously, let us know already which formula we're going to use. Approximate the rate of growth he will need to achieve his goal. You will need to achieve his goal. All right. Okay, so if you're still writing, feel free to press pause so you can take your time and finish writing this question. Okay, but we're going to go ahead and start solving this one. Okay, now you can look at when they say approximate the rate of growth. That just means, in other words, solve for R. Okay, so you could say approximate for rate of growth, find the rate, the interest rate. They could tell you anything at all, but the rate of growth is the same as saying your rate. Okay, so the first thing we're going to do is we're going to find everything that we need in this problem. Okay, so we know it's already compounded continuously. So we have A equals P times e to the RT. Okay, so we know if it's compounded continuously, that's the formula we're going to use. Okay, so now let's find out exactly what everything is. Okay, so if it's compounded continuously, remember the A, that's your new amount. So that's $18,000. That's your new amount. Because remember, that $9,000, that's the amount he invested. That's your starting amount. So the principal is $9,000. That's your starting amount. Okay. Okay, so that's the amount he started with. That's the amount he wants to finish with. So that would be your new or your final amount. Okay. Now your R, we have no idea what that is, so we'll make that a little old question mark. And your T, your time in years. So remember, your time, they didn't really tell us how many years, but we do know that it's going from age 18 to age 30. Okay? So we can kind of figure out how many years. So we have 30 minus 18. That means that your time is equal to 12 years. Okay, so even though they didn't give us the time, we can find it. Okay, so they gave us everything we need here to solve this problem. All right. So let's go ahead and slide this up a little bit. Okay, so if we use this formula and we replace it, A is equal to 18,000. So if 18,000 equals, our principal is 9, so we have 9,000 times E to the R times T, so that's R times 12. Or you can make it as 12R. Make it R times 12 or 12R, either one. Okay, so all we did was plug in everything that we found out into our formula. Okay, and just like before, your very first step to solve is to isolate your E value. So we're going to go ahead and divide by 9. So remember, first, we're going to isolate. Bring that up some. So if we divide both sides by 9,000, we have 18,000 equals 9,000 e to the 12r, divide both by 9,000. That means e to the 12r equals 2. Okay, so now we have our second step. Okay, so we apply our natural log. Okay, so if we have e to the 12r equals 2, that means you have natural log of e to the 12r equals natural log of 2. All right, so the natural log and the e here cancel each other out. So we end up with 12r equals natural log of 2. Okay, so if we divide both sides by 12, moving that up a little bit, we end up with r equals natural log of 2 divided by 12, which really doesn't help you much. But that does give you your exact answer. But if we plug this into a calculator, we have r is approximately equal to 0.058. Okay, which is your decimal answer, but in most cases they're looking for a percentage rate. So to convert a decimal to percent, you move the decimal point over 2 spaces to the right and add your percent sign. So your rate will be approximately equal to 5.8%. Okay, so that would be the interest rate he'd have to find if he wanted to turn his $9,000 at age 18 into $18,000 by the time he is 30. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our next example. All right. move this one out the way. Alright, so let's say for this example, let's say Sam invests $4,000 in an account that compounds continuously or compounds interest continuously. That may be, and let me go ahead and clean that up just a bit. That compounds interest continuously. And earns 5.5%. Okay, so how long will it take for his money to reach $80,000? I'm about to say $80,000. Okay, so Sam invests $4,000 in an account that compounds interest continuously and earns 5.5%. How long will it take for his money to reach $80,000? All right. Now, this is whenever you see how long will it take or something like that, that's basically the same as saying solve for time. Okay, so whenever you see how long, they're basically just saying solve for t. All right. So if you're still writing, feel free to press pause. Actually, better yet, I want you to press pause and try to solve this one on your own because it's pretty similar to the problem we just did. So I want you to try this one on your own. Alright, so assuming you've pressed pause and you've worked this one out, let's go ahead and verify your answer. Okay, so you see it compounds continuously, so we already know which formula we're going to use. Okay, so now all we have to do is find all of our values. Okay, so we know our new amount is $80,000. Okay, now our starting amount, remember he invested $4,000, that was the starting amount. So your principal is $4,000. See, that's always going to be the key difference. You want to know the difference between your new amount and your starting amount. Okay, now your interest rate is 5.5%. But you have to convert that to a decimal. Remember, if you want to convert a decimal to a percent, you move it 2 spaces to the right. To convert a percent to a decimal, you move it 2 spaces to the left. So this is actually 0.055, not 0.05. Okay, so 0.55. Let me see that in there. We go. And our time We don't know because that's what we're solving for. Okay, so we have everything we need to solve this right here. Okay, so A equals P times e to the RT. Say that 5 times fast. Okay, our A is equal to 80,000. So that's 80,000 equals, your principal is 4,000 times e to the power of r times t. So that's 0.055 times t. Okay, so we just went ahead and plugged everything in from that problem. All right, so we divide both sides by 4,000. So remember, that's our first step, is we isolate. So 80,000 equals 4,000 times e to the 0.055 times t. Divide both sides by 4,000. Where those two cancel each other out. That leaves us with e to the 0.055 t equals 80,000 divided by 4,000 is 20. Okay, so that moves us to our second step. Oh, move that up some. Where we apply our natural log. Okay, so if we have e to the power of 0.055 t equals 20, that gives us the natural log of e to the 0.055 t equals the natural log of 20. Okay, so remember, your natural log and your e will cancel each other out. So that leaves us with 0.055 t equals natural log of 20. So if we divide both sides by 0.055, that means t is equal to natural log of 20 divided by 0.055. Okay, which is your exact answer. But if we plug that into a calculator, then t will be approximately equal to 54.5. Okay, so it will take approximately 54.5 years for $4,000 to become, move that up some, $80,000 at 5.5% interest compounded continuously. Okay, so of course, if you compounded it so many times annually, you'll get a different answer. If you had a different percentage, you'll get an answer, different answer. So with those particular details, it will take approximately 54.5 years. All right. So if you are still writing, feel free to press pause. But we're going to go to our next example, which will cover exponential growth and decay. Okay, so I kind of wrote this out for you. All right, so really the only difference between exponential growth and decay and the compound interest formula is that we don't have the P and we don't use we don't use R. Okay, we just kind of change our variables. Okay, but everything is kind of the same general idea. Okay, so here We have A equals our final amount. Okay, remember it's final amount or new amount. Our A sub 0 is our original amount. Remember before we had a P. Okay, so that would be our starting amount or original amount. We're just using A sub 0 as our original amount. Okay, again, T is equal to time, and K is equal to your rate of growth if K is positive, or your rate of decay if K is negative. Okay, so it all depends on whether or not K is positive or negative, and that will tell you if it's a growth or decay. Okay, but other than that, it's the exact same general idea, even though it's not the exact same thing. Okay, because the rate of growth can be positive or negative. All right, so if you are still writing this, feel free to press pause. If you want to write down your formula, but let's go to our example so you can see how this all fits in. Oops, let me straighten out my paper here. All right. So let's say, for example, say you have a certain bacteria declined from 100,000 to 100 in 24 hours. Okay, so over the course of 24 hours, you went from 100,000 of these bacteria to only 100. Okay, so at this rate of decay, how many bacteria would there have been at 16 hours from the start of the experiment? Okay, I'll give you a couple of seconds to pause this one and finish writing this down. All right. Okay, so we're going to go ahead and solve this one. Okay, so we can see already that this is going to be a rate of decay problem. So we're going to use our A equals A sub 0 times e to the power of kt. All right. Now this one's going to be a little tricky because it seems like I'm going to show you how you have to solve it, even though it looks a little different. It looks like you want to solve it one way, but that wouldn't be the correct way if you think about it, but I'll show you what I mean by that. Okay, so our A, our final amount, this is tricky because remember, we started with 100,000 and we declined to 100. So 100 is our final amount. That's why I say you have to be really careful with this one. And A sub 0 is 100,000. Okay, that's our original amount. Okay, so now our rate, we don't know what our rate is, so we're going to get that. Now this is where it gets tricky. Our time is equal to, we can't use 16 hours because this question says, what is the rate in 24 hours? So we have to find the rate first for the 24 hours before we can find the rate for the 16. Okay, so here our t is equal to 24 hours. That's why I say you want to be really careful with this one. Because when they're saying it's at this rate, they're basically saying if you find the rate using everything here, then what would that amount, or what that rate be, or how many bacteria would be left at the end of 16 hours. Okay, so that's why you have to find this first. So if we plug this in, our A, so we have 100 equals our A sub 0, so we have 100,000 times E to the K times T, so it's 24K. Alright, so if we go ahead and divide both sides by 100,000, we have 100 over 100,000 equals 100,000 e to the 24k over 100,000. Okay, so we just divided both sides of this by 100,000. So that cancels out. So you have e to the 24k equals 100 divided by 100,000. That simplifies to 1 over 1,000. Okay. So remember, that was your first step, to isolate. And your second step, to apply the natural log. So if we apply the natural log to both of those, we have the natural log of e to the 24k. I'm about to forget to write my e there. We have the natural log of e to the 24k equals the natural log of 1 over 1,000. Okay, so your natural log and your e cancels each other out. And I'll write this underneath it to avoid getting confused. So you have 24k equals the natural log of 1 over 1,000. Don't need that there. So if we divide both sides by 24, you have k equals natural log of 1 over 1,000 divided by 24. Alright, so we have our rate. We're going to hold off on making that a decimal. You can make it a decimal approximation if you want to, but the only problem is once you approximate it, depending on how many decimal places you have, you'll get a different answer. So that's why it's best to leave this as an exact amount for now. Okay, even though it would be so much easier just to make that into a decimal, but it could give you the wrong answer. So we'll leave this for now, and that's the K we're going to use to find out what it would have been at 16 hours. Okay? Okay, now find the number of bacteria when t equals 16. Okay, so now that we have our rate, it's a complicated rate, but it's a rate. We now find the value when t is equal to 16. So really, we use everything up here that's exactly the same, except we replace the k with that value. And the 24, we replace that with 16. Okay, so we have our A equals A sub 0 e to the kt, that's going to become, remember our A is 100. Well, actually, now A wouldn't be 100 because we have to solve the final amount. See, that's after 24 hours. Our A is now going to be a new value. So A is going to equal A sub 0. So you start off with 100,000 times E to the K times T. So that's going to be to the natural log of 1 over 1,000 divided by 24 times T, which is 16. Okay, so remember, we're going to have a different final amount because now we're looking at what would happen if our T is equal to 16. Okay, so if you plug in 100,000 times e to the power of this entire value, that's why we didn't want to do a decimal approximation just yet. Because if you approximate that to a decimal value, once you multiply it by 16, your answer will be skewed just enough to maybe give you the wrong answer. So if you plug this into your calculator, you end up with A is equal to about 1,000 bacteria. I'm looking at the wrong value. So A equal to about 1,000 bacteria after 16 hours. Alright, so again, it can get a little bit tricky, but the first thing you want to do with a problem like this is find your rate with the time that they gave you. And then you want to find your new amount, given your new time, or the time that you want to find it at. Alright, so hopefully this video made sense, and I will see you on the next video.